Welcome to the Rise Inside podcast, hosted by Justin Starbird and powered by Rise Robotics. Listen as host Justin talks to experts from the Rise team about topics relating to mechanical engineering, industrial design, commercialization, and innovation. True collaborations work when ideas are integrated at inception to solve significant problems. Rise Inside brings together how the team continues to work with great folks to commercialize ideas. You're listening to the Rise Inside podcast. Here's your host, Justin Starbird.
Welcome back to Rise Inside. My name is Justin Starbird, and I have the distinct pleasure of welcoming back one of the founders of Rise Robotics. Blake, welcome back to the show.
Thanks, Justin. Happy to be here.
Today is pretty neat because you actually brought some other Rise guests with you. Tell me about who do you have with you?
I did. We have two of our senior mechanical engineers, Toshan and Emily, joining us today to talk about one of the projects they've been working on in the past few months.
Great. Well, Toshan, Emily, welcome.
Thank you. Good to be here.
Likewise. Thanks for welcoming us.
Yeah, man, this is wonderful. It's always great to hear, the stories and the different things that are going on, at Rise, and hear in a first-person perspective. I know, Blake, you and I have gotten to talk a lot about the history. I got to talk to some investors recently as well as some partners. But what you guys are doing is pretty neat. So, from your perspective, tell me a little bit about Rise and what you've been working on.
Sure. So we have our first commercially launched product is right on the cusp of being released. We just took it to a trade show last month, and it is ready for pilot. So we are right now demoing it for customers, to customers, with customers, and we'll be launching it as quickly as we can. That liftgate product uses a 4,500 pound cylinder, which is probably the smallest one that we will be offering for some time. And the group that is here today has been working on a much larger cylinder, which, while it doesn't represent the absolute higher end of what we're capable of, it is definitely getting there.
That sounds awesome. How was the trade show? How was the initial commercial product received? I know we've been to a couple of shows now. What was the feedback so far?
Yeah, I think we were hopeful and we had high expectations for the show. We really hoped to kind of make a splash and to get, the attention of the right people. And it definitely exceeded all of our expectations. We were solving real problems, getting to the root of them. We're not solving them in superficial ways. And I think it really shows, and it evidences itself with the quality of the product and the experience overall. So I think we definitely got at least as much sort of attention and thought and discussion and visits as we were hoping for, which is fantastic.
That's awesome. So, the story on everybody's mind, especially when we're talking about, a smaller class initially, is what's next for Rise.
Yeah, we're working on cylinders that are across the load spectrum. So again, 4,500 pounds is probably on the smaller side. We can go larger than 50,000, up to about 100,000 is doable just with commercial off-the-shelf components. But there's a class of cylinder that is around 50,000 pounds that has utility across a variety of applications. And so we've been developing one in the lab.
Toshan, you want to tell me a little bit about, what your role in that has been?
Yeah, so I was brought on initially coming from Desktop Metal and Terrafugia to kind of spearhead the development of this new actuator. And initially, I think the thing that we were trying to address was there was a lot of skepticism around the word actuator and its ability to actually scale, to be considered something that would be used in the heavy machinery industry. And that's something that we really wanted to address. Some of these concerns were around, were kind of like fed by ball screws, lead screws, where when you get to a really large ball screw or lead screw at really large strokes, one is you can't go at really high speeds because of resonance issues. The other thing is also when it comes to some of these environments that these might operate in, like when it comes to like shock loading or dust or particulate based environments. Ball screws, they have like these point loadings with ball on metal surface contact. So they're not as friendly with shock loads. That's where some of our technology really begins to shine, where if you take our belt through the 10:1 wraps, it kind of acts like this giant spring. And it kind of wedges its way in between hydraulics and conventional linear actuators. So our goal is to redefine the importance of actuators and where it stands in kind of the heavy lifting space.
Great. And Emily, what is your role here at Rise now, and especially related to this project?
So I was brought on because when we started this project, we learned that we needed more engineers to work on it. So
Oh, you mean you need people to do the work? That's exciting.
Need help. So I was brought on to help specifically originally with this project. So I did help with a lot of the design work, the creating the drawings, and eventually the assembly and putting up the demo and the test assembly up in our lab.
Very cool. Well, let me ask you, does the efficiency of starting at, 4,500 pounds or 5,000 pounds, does it scale the same way once you get to, heavier weight and more difficult tasks with like 50,000 pounds and even the 100,000 pounds that you mentioned?
Yeah, so that's a great question. And a lot of the factors actually scale pretty linearly. We might have had some concerns initially with the inertia of the sheaves as they got bigger and bigger. That might play a role, but we found that the efficiency actually got better because we had better tribological interfaces, and we landed up using better motors and gearboxes and also the inverters. And we found that we exceeded our expectations pretty significantly.
Yeah, like that must make you happy, right?
Absolutely. And to touch on some of the specifics that Toshan mentioned that do scale really well, a number of them are essentially non-dimensional parameters. So as an example, if you take a bearing of a certain type of construction, full complement, cylindrical roller bearings, a bearing that is about twice as wide and twice as large in diameter will have approximately 4 times the load capacity with the same expectation for fatigue life. That just has to do with the contact mechanics of the steel and the hardness of the material, which is maintained throughout the range of bearings. Similarly, the belts themselves are able to interface with their respective pulleys at a certain amount of pressure, which is somewhat analogous to the pressure that is contained within a hydraulic cylinder. And that too, the ability of the material to sustain pressure, contact pressure, is more or less the same across the size range of material. And it's well in excess of 1,000 PSI, which is what allows us to make cylinders that, while they may not be exactly as compact as hydraulic cylinders, they are comparable in size.
Absolutely. Yeah. Now, one question that I got, everybody that listens to this is going to ask themselves is, does this cost to scale as well? Does it go up exponentially when you're able to actually, lift that much weight?
Yeah, that's a great question. And I think we can answer it a few ways. The first is cost is typically broken down into materials and processing of those materials. And from a materials standpoint, we use significantly less material, particularly steel, in our designs. And that simply has to do with the fact that you have 2 principal steel assemblies, or assemblies containing steel components that are load bearing with bearings inside. And then you have belts spanning the distance, and everything in between is just air. So when you compare it to either hydraulic systems, inclusive of their pumps and valves and all of those things, or to screw-based systems, we use less material and therefore save in that dimension. And then on the processing side of the equation, turned components, so CNC turned components, are typically much easier to produce than other more complex assemblies. Yep. So screws, for example, require really highly sophisticated custom machines, particularly for grinding operations, that are meant to manufacture a certain size of screw. And you can't just make a bigger screw necessarily with a particular grinding machine. So we are able to use conventional machines that fabricate our parts in a way that is that takes advantage of existing machines without requiring the necessity to make new manufacturing machines.
And for you guys, Emily, Toshan, does that make your job easier?
It directly translates to lifting lighter components when assembling something. So in a sense, it definitely does. Also, one thing to tie back into the cost, we found empirically as we get to a higher class of cylinder, we actually reduced our dollar per load cost, so it gets cheaper to lift heavier things.
Oh, okay. Well, let me ask you, and I'm not sure who this would be directed at, but how are you able to prove this technology to potential customers and potential partners?
Well, we have to test it and demonstrate it on every level. So we have to start at the component level with the belts and the bearings and show that those work in isolation to prove the basic tribological interaction. Then we have to test all of the subsystems, all of the pieces on a slightly more aggregated scale to make sure that everything fits and functions accordingly. And in some cases, do durability testing of those components. We also have to test the full cylinder system. So we test our cylinders in isolation on a test stand just to get as many miles on them as possible. And then also, of course, test the full machine. So we have a full-scale truck with a liftgate on it, moving around the planet, lifting and lowering things right now.
I think that's so cool. It is so neat to even to talk about, but also to see in operation. What are your partners saying about that? I know, right now, one of the things that you're doing is because you're able to actually charge a battery while it's lowering a load. Does that impact the battery size later? And what are your partners saying about the success that they're having so far?
So that's a great question. And when we actually went to measure the efficiency of our actuator, we found that in lifting, we are about 80% efficient. And when it comes to lowering, we can regenerate about 72% of the potential energy. Now, if you were to compare that apples to apples, the application over here was a high capacity forklift. And during the start of this project, we basically measured the hydraulic version of this forklift. And we found that on average, the lifting efficiency is around 30%. And for lowering, it actually consumes a considerable amount of energy. And that's due to this thing called a counterbalance valve. Basically, the idea is to maintain hydraulic pressure while lowering, so as to have a controlled lower. And when we kind of ran this study through the typical use case, we found that we were able to save as much as 90% of the actuation energy, which was extremely significant. And if you would translate that into like rough numbers, we would find that it would basically reduce the battery size in half or give you twice the runtime.
And Emily, let me ask you, does this translate into it being a safer product, or are there, safety concerns that you're actually eliminating by, having less moving parts and an easier apparatus to work on?
Yeah, potentially there could be some good implications for safety. There's some also good environmental implications that we have. We don't have to use any of the oil that is hydraulic fluid, that is typically used in hydraulic cylinders. Also, when we've run our demo in the lab, everyone who's watched it has commented about how much quieter it is than typical hydraulic cylinders that are in operation, which is very good for noise reduction if you have a lot of noise pollution in certain areas.
Absolutely. There's so many different things I want to ask you about, because but Blake, you mentioned some of the tests. Toshan, you talked about some of the testing as well, and Emily, you're talking about what some of the comments are. You're literally making up new tests though to actually verify some of this data, right?
The thing is, when releasing a new product to market, especially when challenging an industry that's been around for hundreds of years, the hydraulics industry has had a plethora of scenarios to kind of work through all the safety implications or different use cases. So we, in essence, have to kind of distill what will be all the scenarios that our actuator has to face, and what are the things that we have to design around. Of course, that completely feeds back into testing and informs that whole continuous improvement lifecycle.
Yes, and to touch on one specific aspect of safety, the belts that we use are reinforced with wire rope. So it's a full stranded wire rope, some array of those ropes inside of each belt section. And it's a demonstrated safe material that is lifting people in elevators all day, every day. And it is common practice within both the elevator industry and elsewhere when using these belts to monitor them electrically. And because you have steel stranding that is within a polyurethane jacket that is electrically isolated from both the environment and the strands each from each other, you're able to detect essentially changes in that in that isolation, in that electrical isolation. So if you have a steel strand that is exposed, we can detect that in certain ways. If you have a steel strand that is broken, you can detect that a different way. And if you have steel strands that are in contact with each other, you can more or less, find that out electrically in a third way. So one of the really nice aspects of the set of materials we're working with is that they permit us to monitor them in ways that are much easier than hydraulic valves and also hydraulic hoses. There are a few companies that have tried to do, quote unquote, active monitoring of the state of wear of a hydraulic hose. LifeSense is one that comes to mind, but for the most part, these products don't really find their way into commercial applications. And if a hose does break, it breaks rapidly and quickly and disastrously.
Right.
And by contrast, we can monitor the materials and watch them and observe them over the course of a very long period of time in an automated fashion without human intervention, and then simply report back that state throughout the life of the machine.
That's so neat. I was actually speaking with somebody just earlier today about the lift gates, and they were a user. They were one of the so your partner Anthony Liftgates. They sell their apparatus at the end, to many customers all over the country, and they were doing some research just recently in to being able to position the Rise cylinder in their products properly, right, on the sales side. And so one of the elements of feedback that they got was that one of their customers was replacing almost every element of the lift gate that is in use every couple of months, and it was costing them a significant amount of money. And because, like, to your point, it was preventative maintenance. There was no way to accurately predict when there would be a failure. Tell me about some of the demos that you're doing now that makes it possible to scale the technology. I know we've talked a little bit about elements in and around it, but talk about some of the demos that you're actually sharing so that folks can understand what's really going into this.
Yeah, I mean, to touch briefly on that point you brought up about preventative maintenance, essentially most hydraulic systems nowadays are still, quote unquote, not smart devices, and they're either in an operational state or they're in a failed state, one of a few different options depending on the circumstance. And there's really no easy way to monitor them. It is certainly possible to add pressure gauges and flow meters and things like that to a hydraulic system. It isn't done very often, although never say never, as the saying goes. But you just don't find these things in commercial application. We aren't paying a huge sum of money in extra sensors to monitor our stuff. It's kind of inherently part of the whole endeavor. That access is part of what we're doing. Really the only solution to a complex system that has multiple failure points, if you really want it to not break, the only thing to do is to replace the components across the spectrum on some time scale that is a small fraction of the mean time to failure. And that's what they're doing. So they're spending probably 3, 4, 5 times more on these components than they would actually have to, replacing them again 3, 4, 5 times sooner than they would need to in order to guarantee that there isn't a failure. So we're kind of turning that conversation completely on its head, very much following the trend towards telematic systems and towards self-monitoring systems. But we just have this inherent advantage where the materials and methods that we use are monitorable. And that's a thing that you can't really just make up. It just sort of is or it isn't. And in our case, we have that advantage.
There's also a secondary part to, I don't know if you've had the experience of replacing hydraulic seals, but
not today. It didn't happen for me today, but
it is a pretty obnoxious experience. And hydraulic oil is not a friendly fluid. And there's like many gallons of that in a machine. that need to be removed, disposed of in an environmentally friendly way. Replacing all the seals is a very work-intensive, laborious process, and it takes a huge amount of downtime. Wherein Rise Technology is aiming for its belts to be replaced through a pretty seamless process. Also, when it comes to replacing the greases with the bearings, we're going to have standardized grease fittings that will allow us to flush greases to continue the extended operation of these machines.
The seals and the wear bands in particular are very hard to get to. They're deep within the machine. You essentially have to rip apart the entire cylinder and deconstruct it in its entirety in order to get to them. There are some seals that kind of come in sections, 2, 3, 4-part sections that allow you to kind of come circumferentially around a rod or a piston or a cylinder. They're extremely rare, and they certainly don't apply to hydraulic systems. You have to be able to really take the whole thing apart to get to them, and it's what makes it such a pain.
Well, we were talking I asked you a little bit about the demo that you've been doing, and what the difference has been between working on the 4,500 pounds, 5,000 pounds to 50,000 pounds, and then you proved that you're able to scale the technology. If you break that down into the different elements, you want tell me a little bit about that demo?
Yeah, sure. So we have 50,000 pound demo that can run today in our lab, and we kind of got to that. We wanted to make a bigger cylinder, but we didn't want to make a bigger cylinder just to be bigger. We wanted it to be useful as well. So we worked with a high capacity forklift manufacturer to develop a 50,000 pound cylinder, because that is the cylinder that would be most helpful in their application. In a similar vein, we also worked closely with a lithium-ion battery pack manufacturer to make sure that the power source that we were going to use for our cylinder is something that could be used in the industry as well. Through those relationships, we were able to not only acquire the battery, but also acquire a test stand using an actual high-capacity forklift mast that we could rig in our lab to test the cylinders. So we do currently have that running in our lab. We can run it up and down without weight. It's pretty exciting to see.
So let me just level set. 50,000 pounds. What are we lifting with 50,000 pounds? I mean, a car is only, a couple thousand pounds. What are we lifting?
So currently what we're using in our lab to lift is we created molds that we poured concrete in. So we basically just stack a whole bunch of concrete blocks, like huge concrete blocks, 4 feet by 8 feet,
Yeah.
and about 6 inches tall concrete blocks that we just stack on top of each other on the forks of the forklift.
Yeah, it was a pretty interesting experience. None of us had really poured concrete before, and then oh, the concrete truck is showing up, and we've got these molds in our parking lot, and we had to kind of stop traffic to get the truck to come in, and then
And I've been to that. I've been to your parking lot. It's not easy to stop traffic.
Right, yeah.
And we all kind of just grab shovels and we're like, okay, we're going to move the truck back and forth, pour the concrete here, and then you use this plank to flatten it. I'm going to use the shovel to spread this, and kind of got our hands and feet dirty.
That's great. So in the market, what are some examples of 50,000 pounds that they're lifting in real use cases?
The high capacity forklift is actually rated to 36,000 pounds. Basically what this forklift would lift would be, so if you were to take a certain version of this in marinas, you would basically lift boats out of the water.
Oh, yeah.
Say about 20 to 50 foot long boats, and then stack them in this kind of giant grid matrix. Other things that you could lift that are that size would be general material handling, like metal stock, whether it's wood or trees, basically all of the different material handling industries where the load's not really defined. It's not a particular package. And this might be the high capacity forklift, but the same kind of actuator development is kind of targeting also the container handler market. Where basically there'll be a giant machine which is kind of like a mobile lift or a mobile crane, which will grab these giant containers and then stack them in shipping ports.
That's so cool. What's been the most fun part of doing that, other than moving the molds, of course? Is it to see that like you're actually creating something that does it?
My favorite part was the assembly. When we started actually getting all the parts in and started putting it all together. One of my favorite things to do while we were assembling is once I had a sub-assembly for the 50,000 pound actuator, I would put it on a table and then go grab the exact same part from the 4,500 pound forklift and just put them right next to each other to kind of see the scale. But also, this one is a whole lot bigger than the other one, but it's pretty much the exact same thing for the most part. The scalability was really cool to see in that way.
Yeah, you might ask what is incremental change for RISE, and what we view that as is 10x, an order of magnitude.
Yep. How about for you, Blake? You got to see, one of your visions like come together.
I mean, it's always a joy to see the machine in motion. There was a time that the Toshan in particular was working on the software and electrical side of things to get the motor inverter and the battery up and running. And the first time a thing moves and comes to life, I think that's always the most exciting. And many kind of shared that experience. We also got to crush cans occasionally, which was fun.
Yeah. That's so awesome. So what does this mean for industry? What does this mean for the different industries that you're working with? You've talked about lift gates, we're talking about forklifts, but what does this mean for those industries? This means we're totally changing it, right?
It does. And what we're really striving to do here for the material handling industry in particular is to change the cost equation for electrification. We're trying to take something that might have seemed insurmountably expensive and to make it accessible. And we're targeting mainly machines that have a 1 to 4 high power lift cylinders in the mast. So, we are particularly well suited to swapping out lift cylinders. We can do other types of cylinders as well with a little bit more effort, but we're really focusing on material handling. And what it will come down to at the end of the day is that we're able to achieve the result that people are looking for the cheapest way possible. And in some cases, we might be the only option in terms of electrifying a particular machine.
That's so cool. Last question for you guys. What does the collaboration process look like now when you take your team of superb engineers and really scientists that are actually figuring all this out? What does that look when you actually get to work with a new partner?
So basically the collaboration process or the new product introduction process is a multi-fold process where initially we'll get talking with the partnering company. We'll try to understand their needs, their key problem areas, and then we'll basically try to take our actuation solution, see where it would apply in their system. Depending on the application, we might conduct some testing, in the field testing. And I'm sure Emily has some pretty interesting stories of going to Air Force bases and testing a plethora of machines. And she can tell you horror stories about hydraulic fluid. So that testing information will basically kind of give us like the heat map of where is all your energy being lost. And that will give us the idea, okay, this is where we should zero in. And we'll create this feasibility report that if you were to replace these components that are having these many losses with RISE technology, this is what you would save in your total cost of ownership. And we would also do a project plan to figure out, okay, this is how much the price per actuator would cost per actuator would roughly be. This is what the development cost of the program would look like. And that all kind of gets baked into that total cost of ownership. Mm-hmm. And then Blake, if you would like to interject onto the remainder of that new product introduction process once we start moving the product into the engineering pipeline.
Right. So once we have a set of requirements in the form of a product requirements document, we translate those into engineering requirements, specific testable requirements that can be listed in a spreadsheet. and then we proceed to architect out the product and to design it according to those expectations and those test requirements, and then to proceed through a fairly standard product development process. We're not trying we are not trying to innovate on the product development process itself. We are just trying to execute it well. To touch briefly on the total cost of ownership point that Toshan just brought up, it's interesting to note that the costs associated with actuation are multifaceted. So we're not just talking about the cost of the battery itself, which is more or less what we were pointing to earlier. We're also talking about the cost of the energy directly, which is fairly obvious. We're talking about the cost of the charging infrastructure that is used to charge the machine. Think superchargers from Tesla, they can vary in size, and the more efficient the car, the smaller the charging solution has to be, right? And there's a fourth element in addition to cost of energy, cost of battery, and cost of charging system, which is the depreciation of the battery pack itself. So batteries have a certain useful life, and the more you use them, or in other words, the higher power the device is, due to additional losses, the shorter the battery will last. So if you use it more gently, it lasts longer, therefore depreciates more slowly and saves money in the long term in that dimension as well. So what we'll find is that efficiency saves not once, not twice, but at least 3, if not 4 times over. And that net change to the total cost of ownership is just astronomical. If you think of the amount of money you spend on a gasoline vehicle, the purchase price may seem large at first when you buy the car, but it is a small fraction of what you end up spending on the vehicle at the end of the day. And that's really when the argument is the strongest.
Well, and people get to work with Emily, right? And collaborate with her. Emily, what's it like for you of being boots on the ground too, in the collaboration process?
Oh yeah, it's really fun. Like Toshan said, I've done some testing on so I've done a couple different machines in the field, and that was a very interesting experience to see and take apart some of the hydraulic systems to instrument them and see what the actual efficiencies of the actual machines were. Another fun part of the process for me is when we start talking with a potential partner is when they start to send me their models with all of their hydraulic cylinders in there, and figuring out how to take those cylinders out and replace them with our actuators instead, which is always a fun creative process to go through.
And then put it all back together and make it work again, right?
Yeah.
That's so cool. Well, guys, I'm so thankful you took the time to explain some of the new things that are happening at Rise, what you've been working on, the excitement that's clearly coming from the team, and what's next on the horizon. On behalf of so Toshan, Emily, Blake, thanks guys for joining me. I really appreciate it.
Thank you so much, Justin.
I think we'll have to do this again and talk about efficiencies and talk about some other things as well that we didn't get to. Otherwise, this would be like an hour and a half long.
That's a lot of information.
Yeah. Well, on behalf of Toshan.
Maybe I can, oh, sorry.
No,
Maybe
go
I
for
can tell you how scary it was working with the giant lithium ion battery.
Yes, I think that would be a great case study in another, we'll have to do like outtakes and have you guys all on and be like, oh my God, you're not going to believe this. Right? That'd be great.
You have been listening to the Rise Inside podcast, presented by Rise Robotics. On behalf of our guest today and host Justin Starbird, thank you for listening. Please share your feedback on our LinkedIn page, linkedin.com/company/rise-robotics.